My name is Mohit Bosumia, working as assistant professor in Government Engineering College, Gandhinagar. Topic of the today's lecture is angle and orthogonality in inner product spaces. Let us start with our first slide. First of all, we recall what we have done in our last lecture. We have discussed about the angle between two vectors in inner product spaces. Then we define Cauchy-Schwarz inequality and see the properties of inner product. How we are defining the angle between two vectors? Let V is any inner product space. U and V are two vectors, or any two vectors of V. Then cosine of angle between U and V is defined as inner product of UV upon norm of U into norm of V. Now today start with this properties of norm. Norm is also called length of the vector. For that, U and V are any two vectors in a inner product space V, and K is any scalar. Then first property is norm of U is always greater than or equal to 0. Second, norm of U is equal to 0 if and only if U equal to 0. Third one, norm of KU is nothing but modulus of K into norm of U. And fourth one is triangular inequality. Norm of U plus V is less than or equal to norm of U plus norm of V. If we want to prove this property, then first property is norm of, we want to prove this, norm of U is always greater than or equal to 0. How we can prove this? By definition of norm, norm of U is nothing but inner product of U with U raised to half. And as we know, inner product of U with U is always greater than or equal to 0. So we can write this, it is greater than or equal to 0. Second property is norm of U equal to 0 if and only if U equal to 0. We want to prove this, norm of U equal to 0 if and only if, so we can write double implies U equal to 0. So start with this, norm of U equal to 0 implies it is inner product of U with U raised to half equal to 0. It means inner product of U with U equal to 0. And as we know, this is by using the property of inner product. When you have inner product of U with U equal to 0, which implies U equal to 0. So one side is proved. Now if we take U equal to 0, then immediately we can write this, inner product of U with U is 0. It means we can write here double implies. Now when you have inner product of U with U equal to 0, then inner product of U with U raised to half becomes 0. So we can write double implies here. And when inner product of U with U raised to half equal to 0, it means norm of U equal to 0. Now third property. Third property is this, norm of KU is equal to modulus of K into norm of U. So start with LHS. So it is norm of KU, and it is nothing but inner product of KU with KU raised to half. So using the property of inner product, this K is outside first of all, so it is U KU raised to half. Then it is this, so k into k, again this k is outside of inner product and rest to half. So it becomes k into k square. It is inner product of u with u rest to half. Now it is a into b rest to half. So we can write this, it is a rest to half and b rest to half. So it is k square rest to half and inner product of u with u rest to half. And k square rest to half, it is modulus of k, because inner product of u with u rest to half is always greater than or equal to 0. And on left hand side we have a norm of some property, norm of some vector, and as we know, norm of any vector is always greater than or equal to 0. So k square rest to half never become negative, so we are writing modulus of k, that is norm of u. So this is the proof of property 3. And now last one, fourth, it is we want to prove this norm of u plus v is less than or equal to triangular inequality. So start with this norm of, if we take this square, then we know that it is inner product of u plus v with u plus v. So using the properties of inner product, we can write this u with u plus v plus inner product of v with u plus v. So it becomes inner product of, again using the property of inner product, u plus u, it is u with v plus this is inner product of v with u plus inner product of v with v, and this becomes norm of u square plus, as we know, inner product of uv is same as inner product of vu. By our definition of inner product, our first exams, inner product of uv is inner product of vu, so it is 2 times inner product of uv, and this is norm of now, as we know that norm of u square is always positive, norm of v square is always positive, but inner product of uv may or may not be positive. But if I put here modulus in inner product of uv, then right hand side becomes larger. So we can write this, it is this less than or equal to, it is inner product of uv now using the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality is modulus of inner product of uv is less than or equal to norm of u into norm of v. So using this Cauchy-Schwarz inequality, this is 2 norm of u into norm of v plus norm of v square, and it becomes, which is equal to norm of u plus norm of v all square. So finally we have this norm of u plus v all square is less than or equal to norm of u plus norm of v. Now taking root both the side, we get this norm of u plus v is less than or equal to norm of, and on both the side value is positive, and this is the proof of triangular inequality. Then properties of distance. as we know that distance is defined from norm, because u and v are two vectors in an inner product space V, then distance of uv is defined as norm of u minus v. So let us see the properties of distance. U, V, W are any three vectors in an inner product space V, and k is any scalar. Then first is distance between u and v is greater than or equal to 0. Second is distance between u and v is equal to 0 if and only if u equal to v. Third one is distance between u and v is nothing but distance between v and u. Fourth one, triangular inequality. Distance between u and v is less than or equal to distance between u and w plus distance between w and v. One can prove this property by using the properties of norm. Now, orthogonal vector. Before this orthogonal vector in inner product space, let me tell you what is the meaning of orthogonal. When we speak the word orthogonal, it means we are talking about when two vectors are perpendicular. In R2, when we say two vectors are orthogonal, when they are perpendicular, it means angle between two vectors is 90 degree. Then they are called orthogonal vector. Now let u and v be any two vectors in inner product space, and if theta is angle between u and v, then cos, as we know that the cosine angle of this theta, it means cos theta is nothing but inner product of uv upon norm of u into norm of v. If we take theta equal to 90 degree, then we have this cos 90 degree is pi 90 degree is pi by 2, and value of cos pi by 2 is 0. So we have this inner product of uv upon norm of u into norm of v becomes 0, and therefore we get inner product of uv is equal to 0. That's why we are defining orthogonal vectors in an inner product space in this way. Let u and v be two vectors in inner product space, then they are called orthogonal if inner product of uv is 0. This is one example. Question is, the example is this: check whether the following vectors are orthogonal with respect to the given inner product. In first example, we have given two vectors p equal to x and q equal to x square, and it is from P2, and inner product on P2 is defined in this way. Inner product of P and Q is equal to integration minus 1 to 1. It is Px into Qx dx. For solution of first example, here we have this p equal to x and q equal to x square. So, and inner product of p with q is defined in this way: minus 1 to 1, it is px into qx dx. And we have to check whether they are orthogonal or not. It means we need to find inner product of p and q. That is this: minus 1 to 1 at px is x and qx is x square dx. So it is minus 1 to 1, x into x square, it becomes x cube. And as we know that f of x equal to x cube is odd function, and whenever you have this integration minus a to a f of x dx and your function is odd function, then value of the integral becomes 0. Using this property, we can directly write this value of this is 0 without calculating anything, because x cube is odd function. Therefore, P and Q are orthogonal. Now for second example, here we have given U and V. U is 2 by 2 matrix. It is 1 0 1 1, and V is thus 0 2 0 0, and U and V from M to 2, and inner product on M to 2 is defined in this way: U1 V1 plus U2 V2 plus U3 V3 plus U4 V4. So it is U1 U2 U3 U4. It is V1 V2 V3 V4. So first of all, U1 into V1, so it is 1 into 0 plus 0 into 2 plus 1 into 0 plus 1 into 0. So it is 0 plus 0 plus 0 plus 0. So it is 0, and now U and V becomes orthogonal. Another example. In this example, we have given R3 with Euclidean inner product, and we have to find out the value of K for which U and V becomes orthogonal. For this example, U equal to given this K 1, and V is given this, it is K 5 6, and here U and V are orthogonal. It means inner product of UV equal to 0, and inner product of UV equal to 0, here inner product is defined as Euclidean inner product, so it becomes U dot V dot product. So this is K1 dot, it is K5 6, so it is K into K square plus it is K into 5, it is 5K plus 1 into 6 equal to 0. Our aim is to find the value of K. So this is one quadratic equation. So 6 can be factorized in such a way that addition of the factor becomes 5. So it is 3 2 ja 6, 3 plus 2 5. So K plus 3, K plus 2. So value of K is either K plus 3 equal to 0 or K plus 2 equal to 0, because whenever you have a product of two real number equal to 0, one must be 0. So K is either minus 3 or K is minus 2. For this two value, given vectors becomes orthogonal. For second example, we can apply the same idea. Take inner product of UV0, and both are from R3, and we have to use Euclidean inner product. So take U dot V equal to 0, and you can easily find the value of K. Now generalized theorem of Pythagoras. Pythagoras theorem is for perpendicular vector. Here perpendicular vector, it means orthogonal vector, but here orthogonal in an inner product space. U and V are two orthogonal vector in an inner product space, then norm of U plus V square is equal to norm of U square plus norm of V square. if we want to write the proof of this generalized theorem of Pythagoras, so proof is very simple. Start with this: U and V are orthogonal. As we know, when the two vectors are orthogonal, we can immediately write inner product of UV is equal to 0. Now start with this: norm of U plus V all square equal to, it is inner product of U plus V with U plus V. By definition of norm, we can write this. Now using the property of inner product, we can write this inner product of U with U plus V plus now inner product of V with U plus V. Again, using the property of inner product, it is inner product of U with U plus inner product of U with V plus inner product of V with U, this, plus inner product of V with V. So inner product of U with U becomes norm of U square, plus now inner product of UV and inner product of VU both are equal by our definition of inner product exempts 1. So we can write this as it is 2 inner product of UV plus norm of V square. Now here our vector U and V are orthogonal. So from this, if I write here equation 1, then using this 1, norm of U square, it becomes 0 plus norm of V square. So reason you can write this 1. So it becomes norm of U square plus norm of V square. This is the proof of generalized theorem of Pythagoras. Now one specific example, here we have to verify this Pythagoras theorem holds for the for given vectors. So how we can deal with this type of example? So for first of all, note down what is P, what is Q, it is x square, and write down your inner product. It is given minus 1 to 1 px into qx dx. Now first of all, we have to check whether P and Q are orthogonal. If they are orthogonal, then and then we can verify the generalized theorem of Pythagoras. This is the hypothesis of the generalized theorem of Pythagoras. So first of all, find out inner product of P with Q. It is x into x square dx, and it becomes minus 1 to 1 x cube. As we discussed earlier, this becomes 0. Therefore P and Q are orthogonal. Now hypothesis of Pythagoras theorem is satisfied. So first of all, write down the Pythagoras theorem. It is norm of P plus Q whole square is norm of P square plus norm of Q square. So to find LHS, we need to find first of all P plus Q, and as we know that P plus Q is x plus x square, and now norm of P plus Q all square is nothing but inner product of P plus Q with P plus Q. So it is minus 1 to 1. It is p plus qx into p plus qx. So it is x plus x square into x plus x square dx. So it is minus 1 to 1. It is x plus x square whole square dx. Simplifying this using the formula a plus b whole square, a square plus 2ab. So it is 2x cube plus x raised to 4 dx. Now how we can find this integration? That is norm of p plus q whole square. If we separate this integration over addition, then it is x square dx, 2 outside, minus 1 to 1, it is x cube dx plus integration minus 1 to 1 x raised to 4 dx. So this x square is even function, so it becomes 2 times, and limit is minus a to a, so here minus 1 to 1, so it becomes 0 to 1, and this becomes 0 because our function x cube is odd function. So 2 integration 0 to 1, it is x raised to 4 dx. So it is 2, it is x cube by 3 using the formula of x raised to n. Integration is x raised to n plus 1 upon n plus 1. 0 to 1 plus 2, it is x raised to 5 by 5. Limit is 0 to 1. So it is 2 by 3. After putting the limit, it is 2 by 5. So taking LCM, it is 10 plus 6 upon 15. So it is 16 by 15. Now we want to find norm of p square plus norm of q square. So first of all, this norm of p square, it is inner product of p with p. It is minus 1 to 1. It is px into px, and px is x, so x into x dx, and it becomes x square. X square is even function, so we can write this 2 into integration 0 to 1 x square dx. So it becomes 2x cube by 3. Limit is 0 to 1, so it is 2 by 3, and norm of q square, it is inner product of q with q. This is minus 1 to 1. It is qx into qx, so it is x square into x square because our qx is x square. So it is, and x square into x square, it is x raised to 4, and it is even function. So 2 integration 0 to 1 x raised to 4 dx, and it is 2 integration of x raised to 4, it is x raised to 5 by 5, and putting the limit we will get 2 by 5. Now addition of this 2, norm of q square, it is 2 by 3 plus 2 by 5, so it is 10 plus 6 by 15, so it is 16 by 15. So this here, from this we have norm of p plus q whole square is 16 by 15, and this is norm of p square plus norm of q square, it is again 16 by 15, so both are equal. So generalized theorem of Pythagoras is satisfied. And similarly, for second example, here we have given two vectors u and v, and we have to use Euclidean inner product on R3. So for this example, first of all, find inner product of UV, that is U dot V. First of all, show this two U and V are orthogonal vector. Then we write the statement of Pythagoras theorem and then verify this theorem. Now orthogonal complement of W. Let W be a subspace of inner product space. Let U be any vector in V. When U is said to be orthogonal to W, if it is orthogonal to every vector in W, it means, let me write this. Here V is given inner product space. W is subspace of V. Take any vector U from V. Now when we can say this U is orthogonal to W, if it is orthogonal to every vector in W, it means mathematically it can be written in this way: inner product of UW equal to 0 for every vector W in capital W. This. Then we can write this: U is orthogonal to W. And if we take all the vectors of V which is orthogonal to W, then that set is called orthogonal complement of W. Orthogonal complement of a subspace W is denoted by this notation. It is W raised to this. Now let us take one example. Here we have given W be a line y equal to x in a xy coordinate system in R2, and we have to describe the subspace W complement. It means our aim is to find W complement. So first of all, let me write that what is given and what we want to find. W is given in this way. It is a line y equal to x or x equal to y in xy coordinate system. So first of all, here V is R2 with Euclidean inner product. And W is given in this way. It is the line x equal to y. It means in sat form we can write this: xy belongs to R2 where y equal to x, and this can be further written as it is x comma x belongs to R2. So every vector of W is of the form x comma x. And we want to find the what is W complement, orthogonal complement. So let us take one vector. Let U equal to U1 U2 belongs to W complement be any vector. It means we are taking one arbitrary vector in W complement, and as we know the definition of W complement, this vector U is orthogonal to every vector in W, and therefore we have this inner product of U with any vector, every vector of W. It means every vector in W is of the form x comma x, equal to 0. We have this. So this is inner product of u1 u2 comma x comma y x comma x equal to 0, and here we know that inner product is given on R2 and it is Euclidean inner product, so it is dot product u1 u2 dot x comma x equal to 0. Therefore it is u1x plus u2x equal to 0, and here we have to mention this, it is for every x belongs to R. Again, every x belongs to R. For every x belongs to R. Every x belongs to R. So therefore we have this u1 plus u2 into x equal to 0 for every x belongs to R. Now we have product of two real numbers u1 plus u2 and x. So whenever you have a product of two real number equal to 0, one of them must be 0. But here x is not fixed, it is arbitrary value. So we must have u1 plus u2 equal to 0. Because here we have for every x belongs to R. Therefore u1 u2 satisfy the equation x plus y equal to 0, that is y equal to minus x. It means, and here we have taken u as any arbitrary vector. It means when you take any arbitrary vector in W complement, it is u1 comma u2, it always satisfies this equation x plus y equal to 0. It means it is of the form y equal to minus x. So if we take collection of all such vectors, then it becomes W complement. So W complement can be written in this form. So it is x comma y belongs to R2, and where y equal to minus x. So it is x comma minus x belongs to R2. So this is the way to find W complement. Now properties of orthogonal complement. If W is a subspace of a finite dimensional inner product space V, then W complement is a subspace of V. Second property is the only vector common to W and W complement is 0. It means you have only one vector which is in W and W complement both. And third property, orthogonal complement of W complement is W. It means W orthogonal complement, again orthogonal complement equal W. Suppose we want to prove this property, then first property is we want to prove W complement is a subspace of V. As we know the definition of subspace, first of all we need to prove it must be a non-zero subset of V. Take u equal to 0 0 belongs to V. Then inner product of u with W equal to 0 for every W belongs to W, because inner product of 0 vector with any vector it is always 0. So you can write, we can write this 0 0 sorry, I have to write here 0, so it is 0 bar. I am denoting this 0 bar as a 0 vector equal to 0, and therefore one vector, that is u or 0 bar, belongs to W complement. Therefore W complement is not equal to 5 is a subset of V. Now we want to verify closure property for vector addition and closure property for scalar multiplication. First of all, first closure property for vector addition, let UV belongs to W complement. Therefore inner product of U with W equal to inner product of V with W equal to 0 for every vector W in W. And we want to check whether U plus V belongs to W or not. So for that, U plus V, we have to check this inner product, and using the definition of inner product, this is inner product of U with W plus inner product of V with W, both are 0, so addition of this 0 becomes 0. So U plus V belongs to W complement. And now closure property for scalar multiplication. For that, let K be any scalar, and we want to verify this whether Ku belongs to W complement or not. And again, using the property of definition of inner product, it is inner product of K into inner product of U with W, and this is 0. K into 0, it is 0 for every W belongs to W. And therefore K into U belongs to W complement, and therefore W complement is a subspace of V. Now for second property, the only vector common to W and W complement is 0. For second property B, let W is any vector which lies in W and W complement. It means we take arbitrary vector U in W and W complement. As we know that if U is any vector of W complement, then it is orthogonal to every vector in W, and U is in W complement, so U is orthogonal to every vector in W, and U is also in W, so U is orthogonal to U itself. So we must have this inner product of U with U equal to 0, and as we know that it is nothing but norm of U square, and norm of U square equal to 0, we have norm of U equal to 0, and therefore we must have U equal to 0. and as we are taking U as any arbitrary vector which lies in W and W complement, it means when you take any vector in W and W complement, it becomes 0. It means there is only one vector which is common to W and W complement. And for third property, we can write the proof. One can write the proof very easily. It is orthogonal complement of orthogonal complement becomes itself. Now one theorem, if A is an M cross N matrix, then the null space of A and the row space of A are orthogonal complement in Rn with respect to the Euclidean inner product. Now let me tell you what is null space of A. Null space of a matrix A is nothing but solution space of system AX equal to 0. And row space of A is what? Row space is span of the rows of matrix A. And theorem tells us this null space of A and row space of A are orthogonal complement of each other in Rn. And this is second result. The null space of A transpose and column space of A are orthogonal complement in Rm with respect to Euclidean inner product. Now, what is the use of this theorem? Suppose we have a example like this. Let W be a subspace of R5 spanned by the vectors W1, W2 up to W4, and we need to find the basis of orthogonal complement of W. So in this type of example, what is the use of this theorem? First of all, as we know that W is spanned by the vectors W1, W2, W3, W4, which is same as the row space of this matrix, and we know that the null space of A is orthogonal complement of row space of W, row space of A, that is W. So to find the null space of A, we have AX equal to, we have to find the solution space of AX equal to 0. So AX, first of all, write AX equal to 0. Then this is homogeneous system. So first of all, we have to convert matrix A into row echelon form. So after converting, we will get this row echelon form, and from this write down the equation. And here we have 3 equation in 5 variable. So 2 variable are free variable, and that is x2 and x5. X2, take x2 equal to t and x5 equal to r. You can write the solution, and solution is in this form, and you can write your solution in this form. Then this two vector v1 and v2 form a basis of null space of A, and that's why when you write in row form this matrices, it form a basis of W complement. Today we have seen angle between two vectors, orthogonal complement of a vector, then properties on orthogonal complement, then one theorem and some example how we can apply that theorem. Thank you.